Hi, everybody.
Hello.
How are you, Caleb?
I'm wonderful, Mr. Gallagher. How are you?
Oh, man, living the dream, you know.
Oh, yeah.
How's the weather out there in Western New York?
Little nippy today.
Misty?
Nippy.
Oh, nippy. What's the temperature? So, yeah, what are you having for lunch?
I think it's like around 50.
Oh, 50? So, yeah, what are you having for lunch?
It was a sandwich.
Did you bring enough for the rest of us?
I should have.
Yeah, didn't they teach us that when we were little?
Yeah, they
Well,
did.
all right. Hey, how was that exam?
Not too bad.
Not too bad. Yeah, man, I haven't looked at the short answer part, because there's too many of you and it's an overwhelming chore. But I did look at the multiple choice, and man, you guys are freaking smart. I mean, it's like amazing how I never get these kind of grades. I'm really impressed at how well everybody's doing. It's amazing. It's just like you guys have these amazing futures, I'm sure. So, any comments, questions? What we need to do, you need to organize yourselves into groups of 3 to work on a project. Um, so be thinking about that. I need you to tell me who's going to be in your group. I don't know, how long do we need to do that? A week? Next Tuesday? So get your group sorted out, and you need to work on a project. And then you're going to present it. So all the class sessions from Thanksgiving until the end of the year will be presentations, I think. Then there's only, 3 classes or something. So maybe 4 classes. There's 40 kids, and so that would be, that's kind of a lot. Anyway, we'll figure it out. But for the first thing, I need you to tell me who you want to work with. Okay, or tell me that you don't know anybody and you would like to be assigned to be put in a group. Or tell me that you don't like anybody and you want to be put into a group. So whatever works, okay? But yeah, you need to do an economics project. So let me see if I share with you, if I can learn how to use a computer again. On Moodle, there should be some resources for you. Oh, you know what I'm going to do? Watch this. Oh, that's much better. Okay. Can you guys see my Moodle now? So in the beginning section, before we get to anything, we have project ideas. So you guys are going to need to conduct a regression study. And here is an outline of what I'm going to expect from you. Right? Choose your topic, collect your data, different kinds of data, prepare the data, conduct a regression analysis, and write up the results. So this should be a 5 or 6 page paper done by a group of 3 of you. And it should be a presentation that you will do on Zoom to the rest of the class. Okay? And you should analyze some topic that is of interest to you. You know? Now, this is a financial econometrics class. So very often the topic is like, well, you know, stock prices are dictated by GDP and CPI and industrial production. But you don't have to do that. You know, if you're a baseball player, you could, I see topics like annual salary regressed on home runs and RBIs and errors and whatever. You know what I'm saying? Or, you know, hockey. It could be, so I've seen students do projects like, you know, the number of goals regressed on ice time and stuff like that, you know. So the world is your oyster, but you first pick a group and then you'll tell me what your topic is going to be like a week after that. And I'll tell you that's good or not good, you know. So I wanted to share that with you. And if nobody has any questions, I'm going to just start lecturing on chapter 3. So we're going to, I'm going to lecture on this for a while today, and then I'll stop and we'll look at the problems, just so that you don't have to listen to me all freaking day. You know, God, how bad could that be? So let's have a go here. Sorry. You hit the wrong button and you're screwed, you know? Okay. Multiple regression. So we the first part of the course was simple regression and a review of math. Now let's get into some of the real things that we want to talk about. Multiple regression analysis. We need multiple regression models. The problem with a simple regression is very difficult to say how X will affect Y. With the assumption 4 in the simple regression model, i.e., all factors affecting Y must be uncorrelated with X. You remember that assumption 4? That X and Y must be uncorrelated. All the factors that affect Y must be uncorrelated. That's really unrealistic, you know? I mean, that's just really unrealistic. So multiple regression allows us to control for a number of factors which affect Y, or our dependent variable, yeah? So not just your hours spent studying, but also maybe innate ability and whatever. Okay? Definition of multiple linear regression explains variable Y in terms of various variables, X1, X2, X3, and so on, right? So we have a very similar equation, Y, which is our, what we would call dependent or explained or response, right? And then we have, of course, the intercept. And then we have these slopes for each of our independent variables, the independent, explanatory, the regressors, what have you, right? Whatever you want to call them, and the error term. So, and then the error term includes any disturbances, but also things that are unobserved, like that are not expressly in this formula. Yeah. So this shows how observable variables, other than the variable of primary interest, can be included in a regression. Beta sub 0 is our intercept. Beta sub 1 measures the change in y with respect to x sub 1, holding everything else fixed. So that's the key to multiple regression, holding everything else fixed. Beta sub 2 would measure the change in y with respect to x sub 2, holding everything fixed. That's the cool thing about multiple regression, and that's implicit. Motivation for multiple regression. We can put more factors into the model. We know that your test scores are a function of much more than how much you study, right? So this explicitly holds other factors fixed that would otherwise be in our error term. So let's look at this wage equation. This is more flexible to have more explanatory variables. So wage is a function of education, but also your experience, how long you've been working. If we had simply a single regression with wage and education, experience here would be part of the error term. Yeah. So as you can imagine, education and experience are accounted for in this regression. But what's in here? Maybe innate ability, maybe on-the-job training. These all could be in your error term because they're not expressly put into our regression, right? Now, these are measures that affect education explicitly holding experience fixed. Yeah. So this surely tells us we will be able to measure the effect of education on your wage holding your experience fixed. So this is a significant improvement. Another example, average test scores and per student spending. So using, let's have a look at this. Average test score of a school, beta sub 0, the intercept. Per student spending at this school. Average family income of students at this school. Per student spending is likely to be correlated with average family income at a given high school because of school financing. Omitting average family income in the regression would lead to biased estimates of the effect of spending on average test scores. So using multiple regression allows us to see the effect of per student spending on test scores. The key is that we can hold average income constant by explicitly including it in our model. Not including it in the model means it would be part of the error term because it is. Would you think that that's going to be correlated with expenditures? Average family income is going to be correlated with expenditures? You know what I'm doing, right? I'm looking for the one of you that looks the least interested, right? And then I call on you, and then you say, what? And, but I can't decide. I can't decide. I've never seen such a bunch of uninterested people. Let's talk about this for a minute. We're saying that test scores from high school, yeah? we're regressing test scores on spending at the school and average income in the community. If we had a single regression where we said, let's regress test scores on spending at the school, then average family income would be part of the error term, right? We're not accounting for it anyway. It would be wrapped up in that error, yeah, in our residuals. But we said that the errors can't be correlated with the explanatory variables. So isn't it likely that the average income in a community is going to be correlated with the amount of spending by the high school? Sure, they're going to be very correlated. If you come from a wealthy community, they're going to spend a lot of dosh on you at high school. You're going to have fancy computers and maybe even a freaking swimming pool, right? But that's a function of how much money is in the community. So those things are for sure going to be correlated, okay? So even though we know that they're correlated, by putting average income into the community into the equation, we're able to hold that fixed to determine the average spending on the student and how it affects the test scores. Does that make sense? Good. All right. Hey, let's look at this one. Notice that thinly veiled attempt at being excited. Family income and family consumption. So we have consumption, which we're regressing here on family income and family income squared. Well, hang on. This model has two explanatory variables, income and income squared. Consumption explained as a quadratic function of income. Well, we have to be very careful, right? This is an example of a quadratic relationship. Family consumption is a quadratic function of family income. We must be very careful how we interpret the parameters. We just said that the effect on one variable on the outcome holding the other variables constant. Didn't I just say that? That was explicit in multiple regression. But this doesn't make any sense because if we change income, then income squared must also change. What we're saying in this equation is a marginal propensity to consume is dependent on beta sub 2. So you see, this is a quadratic, shows the relationship is a quadratic, so it doesn't make sense to say, oh, holding this fixed, we want to see what this contribution, we're just showing this relationship as a quadratic form, right? Something probably like this, yeah? So how much does consumption increase if income is increased by one more unit? We see this relationship, changing consumption over changing income, and it depends on how much income you're already talking about. Similar to converting to, remember when we converted wages and years of education, and we converted it to logs, it gave us an elasticity. So this is really what we're talking about is a marginal propensity to consume. And we're going to talk more about this in another chapter, so I'm not going to belabor the point. Here we have another example allows us to tie together all the things that we have been talking about, right? The log of CEO salary is equal to beta sub 0 plus beta sub 1 times the log of sales. So this is an elasticity. When we use logs, we're talking about percent changes. Yeah, so this is an elasticity form. And then we add this quadratic function of CEO tenure with the firm. So we would imagine that that's true, right? It's a quadratic form, as you move out with CEO tenure, the salary increases. It's an increasing relationship, yeah? Model assumes a constant elasticity between salary and sales, and it assumes a quadratic relationship between CEO salary and tenure, okay? So even though this is a quadratic, we're saying that the model is still linear. It's linear in the parameters, not in our variables. So the parameters are the beta sub 2, beta sub 3, beta sub 1, but not in variables, which is sales, tenure, and tenure squared. All right. Let's have a look here. OLS estimation of multiple regression. We have a random sample, X sub I1, X sub I2, X sub I through K, and then Y sub I is equal to 1 through N. So this notation, I is number in a series. J is your explanatory variables. So I'm going to go ahead and assume that you guys didn't enjoy that as much as I did, right? Writing on the whiteboard. That was kind of neat for me, but it must have been awful for you. So I'm going to have to figure out a better way to do this. And I actually have a whiteboard over here that I bought in the spring when the pandemic broke out, but I have to figure out a way to write on it and have you see it as well. So I'm going to just go back to the slides and try and make my way through it. So we have X sub I1. So the sub I, as I runs from 1 through N, is number of observations. So let's go back to an example where we have X. Here we have X sub 1. Well, if we had X sub I1, the I would be series number 1. Yeah. So this is anything. This is generic, but it could be, you know, year after year. Say this is a stock price, and this is consumer confidence or CPI, consumer price index, and this is GDP. So, for example, you would have Y for 2015, Y for 2016, Y for 2017. So the 1 would represent 2015, 2016, 2017. And then come back to where I was. Where was I here? So I would be 2015, 16, 17, right? For the series 1 through, right? 1 for 2015, 2016, 2017, and so on. And then 1 would be the first explanatory variable in the example I just gave you, CPI. And the 2 would be the second explanatory variable, which in the example I just said was GDP. Okay? So just understand the notation. If anybody needs help, let me know. The residuals, of course, this is an estimate of our residuals of U sub I. Notice I for each series, yeah? So this would be the residual for 2015 in the example we're talking about. And notice this equation is really just Y sub I is equal to beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 plus U sub I, right? So it's just rearranged to give us our residuals. So the process is to minimize the sum of the squared residuals, yeah? And think about this like if you took calculus as partial differentiation, you want to see the effect of one thing on another thing, holding the other things constant, okay? So, and that's what we're doing here. This is done by the computer, but this is a multivariable calculus problem to get the best fitting estimates of these parameters, beta sub 0, beta sub 1, beta sub 2, is through the minimization of your squared residuals, right? So that's a calculus problem. But we're not going to do that. The computer does that for us, okay? So interpretation, the slope, beta sub j, is the change in y over the change in x for that explanatory variable. By how much does the dependent variable change if the jth independent variable increased by 1 unit? Maybe this is CPI, maybe it's GDP, in the example I've been going with, right? So more important than the details underlying the computation is the interpretation, and this is the interpretation. The key point is that we can obtain a coefficient on one variable holding everything else fixed. That's the whole story here. For example, we have a change in the estimated value of y, which is equal to our estimated values of beta sub 0 times the change in x sub 1 plus an estimated value of a beta sub 2 times a change in x sub 2. If x sub 2 were fixed, right, i.e. 0, yeah, go back to the notion in your head of a simple linear regression. If x was 0, then there's no effect on y, yeah? So that's the idea. We're saying, well, this variable has no effect on y. We want to know what the other effects are. So let's have a look at this example. College GPA is equal to 1.29 plus 0.453 high school GPA plus 0.0094 your ACT score. So the interpretation here is holding ACT fixed. Another point on your GPA is associated with a 0.453 increase in your college GPA, right? Or you could say if we compare two students, student A to have a GPA in college that is 0.453 higher than that of student B, right? So this is the interpretation here. Or you could go the other way around, holding this fixed. How does this impact this? Holding high school grade GPA average fixed, another 10 points are associated with less than 1 point on college GPA. As a matter of fact, that's kind of misleading because this is actually less than 1/10 of 1 point, right? 0.0094. Hey, what does 1.29 mean? Everybody see that, right? College GPA, the intercept of 1.29. What does that mean?
Would that be your base GPA, like where you start off as?
Yeah, but that implies that the high school ACT and GPA were what?
0.
0. That doesn't mean anything, right? That's nonsense. So we must be very careful with our interpretation. Yeah, the
Yeah.
1.29 just simply means that high school GPA and ACT would have been 0, and that's not at all meaningful for us. So really, thank you, Will. Appreciate that.
Yeah.
All right. Properties of OLS. Properties of OLS on any sample. The fitted values and our residuals, right? Fitted or predicted values, Y estimate, Y sub I estimate, estimate of beta sub 0, estimate of beta sub 1, estimate of beta sub 2 times X sub I 2. Yes, so X sub I 1. And the residuals, of course, we knew this, right? The algebraic properties, we've done this with simple regression. It's no different, yeah? The deviations from the regression line must sum to 0. The covariance between deviations and the regressors are 0, right? And the sample averages of Y and regressors lie on the regression line. So again, I just want to point out, I refers to the observation number in the series. J refers to the different independent variables, right? That's why you only see I here on the residuals, but on your variables, you'd have 1, 2, blah, 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 through K, yeah? I can't believe it's only 3 o'clock, man. I feel like I've been doing this for hours. Now, here's what I want you to think about. You have data for daily data for a year. So you have, say business days in a year, right? How many of those are there? 220. So you have 220 lines of an equation. Maybe you have 3 explanatory variables. So in our notation, we have X sub ij. So X sub I would be the observation number in your year. X sub j, sub ij, the j would refer to which explanatory variable it is. So you can imagine, please, if you will, 3 columns of 220 numbers. Now, understand why I wanted to talk to you about matrix algebra. Because the solution to that is simply a matrix. And the notation associated with that is to say, this is my matrix, and call it P. Yeah? So when you're coding, you could say, instead of putting in 200 lines of 3 different numbers, you could say just P, right? That's why we did what we did. All of you that maybe were cranky about having to do that, I just wanted to reiterate my motivation. Okay? So, where are we here? Oh, partially not. So what does this all mean? Partially not, the interpretation of multiple regression. You can show the estimated coefficient. This stuff that we're going to talk about, I'm not going to ask you to remember, but I'll show it to you. You can show the estimated coefficient of an explanatory variable in multiple regression can be obtained in 2 steps. Regress that explanatory variable on all other explanatory variables, and then regress y on the residuals. So, well, what this says is regress x sub 1 on all the other x sub 2, x sub 3, x sub 4. So instead of having an equation that's y is equal to x sub, beta sub 0 plus beta sub 1 times x sub 1 plus beta sub 2 times x sub 2, you have x sub 1 is regressed on x sub 2, x sub 3, x sub 4, right? And then you're going to regress y on the residuals from that equation. Imagine the guys that figured out how to do this, yeah? So you think they were like in the basement, you know, mixing chemicals or something, but they figured this out, right? So the residuals from this first regression is part of the explanatory variable that is uncorrelated with other explanatory variables, and the slope coefficient of the second regression therefore represents isolated effect on the. This is why it works. So this is, if you're interested, on page 69 in your textbook. And if we were in class, I would write the equation 3.22 on the board, and it say, suffice to say that the estimate of beta sub 1 shows the effect of x sub 1 on y after x sub 2 ... through x sub k have been partialed out, just like differential calculus, multivariable calculus. Okay, so let's talk about the goodness of fit, and then we'll do a problem. Yeah, so I got 3 more slides, and then we'll stop and go in the groups, yeah? Because you like that, right? Right. Goodness of fit. Decomposition of the total variation. So total sum of squares, STT, total sum of squares. This is the sum of the square of y sub I minus y bar, your total sum of squares. The explained sum of squares, that which we know about, right? That is the sum of your y hat sub I minus y bar squared. You know, the square of y hat minus y bar. And the residual sum of squares, yeah. So that's the sum of your u hat. Sorry. The sum of u hat squared. I'm laughing because there was an article I saw this morning that said that feelings were now an acceptable response to math problems, you know, in school. Yeah, this is how the world is changing. So if a train leaves Chicago going east at 70 miles an hour, and another train leaves Boston going west at 100 miles an hour, an acceptable, you know, at what point would they cross? Would they bang into each other? An acceptable answer could be that, well, that question offends you, you know. So now we got that out of the way, the r squared, right? We know r squared is the explained sum of squares relative to the total sum of squares. And we can say, because the total sum of squares is the sum of squares, explained sum of squares plus the residual sum of squares, we can then say that the r squared is also 1 minus the residual sum of squares over the total sum of squares. So if another explanatory variable is added to our regression, r squared can only go up. Yeah? That must make intuitive sense to you. If you're trying, if you're trying to explain something, your test scores, yeah, and you run an equation, you run a regression that includes hours spent studying, hours in the tutoring center, and innate ability, and it comes up with an R squared of 0.6, right? That's pretty good. Well, if you added more stuff to it, even though it may be, how many beers you drank the night before the exam, is still going to improve. The R squared has got to go higher if you're taking things out of the error and putting them in the equation, right? So that tells us that an improved R squared is not always an indication that something belongs in the equation. Okay, and then the last equation on this particular slide, let's have a look. This is simply the R squared is equal to the squared correlation coefficient. So R squared can be shown to equal the squared correlation coefficient between your actual Y and the fitted values of Y, i.e. Y hat. Okay? So let's have a look. Number of times you're arrested in 1986. This is 2,725 men. How many times they were arrested in 1986? And it's regressed on prior arrests that led to the conviction. How many times they were arrested in the past and that led to conviction? How many months they spent in prison? How many times, how many quarters they worked? Yeah. So the proportion of prior arrests increases by 0.5. We have a predicted fall in arrests of, so this is 0.5 if proportion of prior arrests, so that's this. How come I can't? This is proportion of prior arrests here. So if this goes up by 0.5, then this will go down by 7.5 arrests per 100 men. Yeah, that's 0.5 times 0.15 times 100, which gives you 7.5. If the months in prison go from 0 to 12, the predicted fall in arrests is 0.408. That's this prison time, months in prison. So 0 to 12, predicted fall is 0.408. I'm sure if you multiply 12 times this, you'd get this. If the quarters employed increase by 1, you're less likely to be arrested, right? This is data from, if you want to run these kinds of regressions just to practice R or whatever, this data is crime 1 in your data set file, okay? So let's look at this. We're going to add something here. No, here. We're going to add something. So we've got the same equation. Prison time, quarters employed, and what was that one? Proportion of prior arrests, proportion of prior convictions, okay? So we've added average sentence here. Average sentence in prior convictions. And the R squared went up a little bit, yeah? So last one was 413, this is 422. So average prior sentence increases your number of arrests. Wow, does that make sense? Does that make sense? Yeah, Paige is shaking her head, yes. I'm fascinated. So you spend more time in prison, that means you get arrested more often. What's up with that? Oh, I forgot. Everybody send me a chat that you're here. Hey, you know what I found out? I am teaching investments next semester. 2 sections of it. 1 o'clock and 2:30 on Tuesdays and Thursdays, in person, like live, in person. So come on, somebody help me out here, man. You spend more time in prison, so you get arrested more.
Maybe. Go ahead, Joe. My bad.
Go ahead, Joe.
I was just thinking, just because you have to reflect that variable into the equation and has to consider it, that r squared has to consider that correlation, so it might go up just because of that extra variable on the
Yeah, there's no
equation.
doubt that adding a variable to the equation is going to improve your R squared. That's for sure. The more stuff you put in there, the better it's going to fit, even if the stuff doesn't help. But my question is different. My question is, I forget. Here, average prior sentence increases the times you're arrested.
Is it because maybe once that you commit a crime, you're more likely to commit another one?
Yeah, let me go. Who said that?
Me?
Marco, yes, that's right. And the more time you spend in prison, the more likely you're going to make bad friends. Yeah? They're going to mislead you when you get out, right? We see it all the time on the TV, don't we? Okay. That's great. Thank you, Marco. All right. So, even if R squared is small, regression may still provide ceteris paribus. Yes, fine. Okay. So, multiple regression analysis. We're going to, this slide is slide what? Number 15. Linear assumptions. Yeah. So, I'm not going to go there because you're bored of listening to me. And I want to. Do the problem. So we'll share that. And then I'm going to put you in the rooms. Just do problem 1. We'll come back and talk about it. And then we'll call it a day. Yeah. I mean, we've all had enough, haven't we? So let's share, figure out what I'm doing. Hang on. Okay, everybody. So this number 1, using the data in GPA 2 on 4,000 college students calculated by OLS. College GPA is a 4-point scale. High school percentile in high school graduating class. So that if you're 5, it's the top 5% of the class. SAT is your verbal. And so this is the contribution to your college GPA. 2 high school graduates, A and B, graduate same percentile, SAT scores. So you guys go into groups and work on this, and then in like 5 or 10 minutes, we'll come back and talk about it.
How's it going?
What'd you say you got?
I got 2.676.
That's what I got.
All right, perfect.
Same.
So A and B graduate the same percentile. Student A's.
I would think that would be like a positive thing if you have a lower number. Oh, maybe. Because if you have a lower number, that means like you were better in the class, like top 5% of the class. And like in the equation, it says like top 13%. So I would think like,
They did even better.
yeah. What's the 1.39? Is that just the average GPA? Like the base GPA?
Yeah, that's base.
So
Professor Gallagher, what does the 1.392 represent in this equation?
Well, it's not very helpful. It means what GPA you would have if you had zero high school percentile and a zero SAT score. So it's not meaningful.
Okay. So yeah, I guess it means they did well for H-Spurk.
It would, of course, be meaningful when you plug in values for your high school percentile. Yeah, you would have to plug that right in and include that to determine your college GPA. Make sense?
Yeah.
Yeah.
Not a lot of chit chat in this room, huh?
No, we're on,
Calculating it.
yeah, we're on the fourth part of it.
How's it going?
Well, I guess it's going okay. How about for you guys?
Pretty good. Yeah, we finished.
You finished?
Yeah.
Wow. You got even number. That's great. What answers did you get?
So for the first one, because of like
Those are
the,
easy. Do the third and the fourth and the third and the fourth.
oh, we're only supposed to do 3 and 4 of one, or you just want to know the answers for 3 and 4?
No, the answers for one, part 3 and part 4.
Okay. A 0.2072 difference in the GPA for the part 3. And then part 4, 337.84.
Very good. Good. Nice job. This must be too easy for you.
3?
Yep. Yeah, those were the numbers.
Yeah, that was the same one.
How's it going, guys?
Good. We finished all of them.
You did?
Yeah.
Yep.
Okay, then bye. Did I go to 4 yet? Yes, I did. 5, 6. One more and then we'll Hi, sports fans.
How you doing?
Oh man, living the dream, you know. So, how we making out?
Well, for answer three, what we got to do is take 140 times the coefficient. So that would be. I just don't know how to really explain number one. It's kind of confusing.
Yeah, I was just about to ask, can you explain number one a little more?
Then I got 0.207 for answer three.
Yeah. So number one, the high school percentile. Is that the one you mean?
Like
Does it make sense?
yeah, why does it make sense for coefficient or hybrid to be negative? I think I understand it, but I don't really know how to answer it.
It makes sense because the bigger your percentile is, the lower you are in the class. If you're
Yeah.
in
So
the
the larger it is, the lower it is.
5% of the class versus moving down to in the top 25% of the class.
Yeah.
So if you're in the top 25% of the class as opposed to the top 5% of the class, your college GPA will go down.
Okay. That makes sense.
That makes sense?
Yeah.
So it doesn't make sense for it to be a negative. Okay, we're going to all get back together, okay?
Okay. Sounds good.
Dang.
Oh, shoot. Sorry, don't do that. No, don't do that. Yeah, sausage fingered it, you know? My question was, my question is, I'm good. Can I be mean?
Go for it.
Okay, I won't even mention any names, but I do notice that some of you are very slow to join the room and come back. Almost as if you're not even at your computer, really.
573 555.
Hey, Shane, what are you doing outside, man?
My computer's dead, so I had to go outside and get my charger. But I'm on my phone right now,
Oh,
so I had to do something quick.
okay, everybody, see that? That's what we call dedication. Yeah. So I'm going to tell you a story. I used to go, and I still do, usually drive the same kids to New York City, right? I know New York City very well, and I worked in New York City for years. And anyway, there's one kid, and his name is, well, he graduated about 3 years ago. And we would stop at McDonald's on our way to New York City, you know, and back. And this dude, everybody would get back into the van, and this dude would go back in and order more food, you know, and we're all like in the van, smells like McDonald's. And this guy's in line, waiting for his freaking pancakes with sausage and stuff like that, you know. So That's what it made me think of when I noticed that some of you don't quite move as fast to the. Anyway, who wants to do number one? Why does it make sense for high school percentile, the coefficient to be negative?
Because
Don't-
like the larger percentile you are, like if you're in the 80% of the class, then you're not doing as well. While if you're like within the top 5%, it'll be a much smaller number. You're probably doing a lot better.
Yeah, okay, so if you're in the top 5%, you're probably going to get a better college GPA than if you're in the top 50% of the class. Very good. Thank you, Drake. What is predicted college GPA when your percentile is 20 and your SAT scores are 1050?
We got like 2.676, I think it was, something like that.
Oh, that's great, Drake. Thank you. How about anybody else? Did anybody get anything different?
I got the same thing.
7.
Oh, go ahead.
I got.
Jesse? Oh. All right. That looks like a sausage finger answer too.
Nah, JK. It was 2.676. That's what I got.
Yeah, there we go. Okay, great. Thank you. Yeah, so is there anybody that doesn't know how we got that? You're not going to say if you do. Anyway, if you don't, let me know. What's number 3? A and B, they graduate with the same percentile, but one's SAT was 140 points higher. Difference in GPA for these two students.
I got 0.207.
How'd you get that?
I just
Bezor?
I just multiplied the 140 by the coefficient.
Yeah, exactly. That's it, man. That's very good. Thank you. How about the last one? Holding your high school percentile fixed, what difference in SAT score leads to a predicted college GPA difference of 0.5?
We got 337.8.
How'd you do that?
It set the college GPA equal to 0.5 and then divide it by the coefficient.
Is that what everybody else did? What did anybody else do? Does that make sense, that answer for everybody?
Sure does.
Thank you, Caleb. You still can't get your video to work, huh?
No, I had it working, but my computer is dead for the beginning of class, and I called in on my phone.
Ah, okay. All right, man, everybody, that's enough, isn't it? So think about your groups. We need that in a week. And then you'll be thinking about your topic. We need that in 2 weeks. And we'll see you on Thursday. Hopefully I'll have your exams graded.
Thank you.
Sounds
Thank you.
good.
Have a
Thank
good
you.
one. Thank you.
Bye.
Thank you.
Good one.
Thank you.
Thank you, Professor Gallagher.
Thank you.
Pleasure.
I have a question for the groups. You said, do we have a maximum of 3 people or 4 people?
3 people.
Okay. Got it. Thank you.
Right. I can make an exception if there's people that you want to work with because we have such a large class, but I'd like to go with 3 each.
Okay.
Okay?
All right. Thank you very much.
Okay.
I got a question for you. I don't know if you saw this, but I couldn't upload the short answer on Moodle. My computer's like really messed up. I couldn't figure it out to save the life of me, so I emailed it to you. My short answers.
Yeah. Just sec, all right?
What's that?
Just one sec.
Okay.
Yeah. 26, 27, it's not here? 20,
Uh,
28?
let me check here. Because I was having trouble even emailing it to you because I couldn't upload it. I can retry again, right? Yeah, see, I don't have it sent right now. Oh, yes, I do. I've got it on the 25th.
No, I'm talking about question number 27. You don't have an answer.
Oh, I must have sent you the wrong one for that one. Oh, yeah. I was confused as all get out on that one anyways. I probably wouldn't have gotten it right. I'm horrible with those.
Well, send me the right one anyway.
Okay, will do.
All right?
Thank you.
Okay, man.
Have a good one.
Yeah, see ya.